I now present a lecture by Professor Robert Lowe, delivered in November 2024 on the topic of logistic substitution in global energy supply to 2050, using reflections on a recent paper. Robert Lowe is a Professor of and the Chair for Energy and Building Science at UCL, as well as a co-founder of the UCL Energy Institute. He's a physicist with a broad interest in the field of buildings, energy and sustainability, with a key interest in the role of research in the transformation of building energy performance. The lecture was provided during the 4th ERBE seminar event, part of a series aimed at creating critical discussion around buildings and energy. The series is co-organised by the ERBE Centre for Doctoral Training and the CIBSE Young Energy Performance Group, with previous topics including the impact of heat pump deployment on national electricity demand, the readiness of households to adopt heat pumps, and much more. Please do support the series and attend a future event either online or in person. And without further ado, Bob's lecture will begin.
So this is the topic of my lecture. And before I begin properly, I just wanted to say a few words about Jevons. The first time I presented this talk was actually in the Jevons room at UCL. And I just wanted to remind you all, if you haven't already done so, to read Jevons' book, The Coal Question. It was only written about 140 years ago, so it's still quite up to date. And it's one of the most interesting books on energy that you can read. So there we go. Let me see if this works. Yep, okay. So what I want to do today is to talk about some of the factors that drive energy system transitions. This talk springs from a paper that I wrote with Paul Drummond, a colleague at UCL. And the title of the paper was Logistic Substitution in Global Energy Demand. So if you'll find the reference at the end of this lecture, and presumably the lecture notes will be circulated to anybody who wants them. And part of what I'm doing is to reflect on the process of writing a paper like this. So where do the ideas come from? How do you get your ideas to write a paper that can get into a journal? And about some of the interesting twists and turns through the process of writing the paper. Okay, so factors that drive energy system transitions, going back again to Jevons and to people like Malthus, Thomas Malthus, people like King Hubbard and Jean Laharrière, who is still with us at, I think, the ripe old age of 101, and recently published his latest journal article. So this is something. You have decades of aspiration and endeavour in front of you, if this is anything to go by. Poverty and potential and this is technical potential, as a stimulus to innovation, is the second category of drivers. And the third is the availability of an as yet unexploited resource, and the emergence of a new technology or cluster of technologies, perhaps harnessing new physical principles to exploit it. On the subject of new physical principles, some of you may remember the lecture that I gave at the beginning of our block week that you will have attended about 2 years ago, something like that, 1 September. And I talked about steam engines because whenever I have the opportunity, I talk about steam engines. And one of the things to think about here is that, as far as I know, there is no biological equivalent of a heat engine. Biological life on this planet, as far as I know, does not use the heat engine at all. Instead, it uses systems that are much closer to fuel cells than heat engines. So the invention of the steam engine was a very good example of a new technology harnessing an at that time unexploited resource using a new physical principle. Okay, so moving on. Yeah, and by the way, when you've finished reading Jevons, I also suggest that you, if you have the stomach for it, you read Thomas Malthus. Very, very interesting perspective on the situation in particular, the demographic situation in the late 1700s in Europe. Okay, so some more factors driving energy system transitions. Learning, which is typically defined by economists as the fractional reduction in cost per doubling of installed capacity of some category or other of technology. Now, the Industrial Revolution, at some point I'll come into the 20th century, and then I'll move into the 21st century, but not yet. The Industrial Revolution was driven by a 40-fold reduction in steam engine efficiency between the mid-1700s and the mid-1800s, which simultaneously reduced both the specific size and mass of steam engines. Now, we are often used to the idea that if you make something more efficient, it tends to get bigger. Heat exchangers get bigger. Cooling systems on power stations get bigger, and so on and so on. And all of this is true. It is really interesting then to look at the effect of efficiency gains early in the Industrial Revolution, which shrank machines dramatically. And all of this was possible because of the enormous inefficiencies of the earlier steam engines. But learning eventually saturates. And what we've got here is a little graph. I spent the weekend doing this. Let me see if I can work out what's going on here. The vertical axis is the remaining thermodynamically limited efficiency improvement. So that is how many times better you can make a particular class of technology before you hit the limits as defined by, for example, the laws of thermodynamics. And in the case of steam engines, which are the blue dots, you can see what's happening. We're heading down from, as I said, a ratio of approaching a couple of orders of magnitude in the early 1700s. At that point, steam engines were about 50% efficient. Sorry, 0.5% efficient. 0.5% efficient. And simply by raising the operating temperature, or the steam temperature, from 100 degrees centigrade to 110 degrees centigrade, you could something like double the efficiency of the steam engines at that time, because the steam cycle that they were working with was so crude and inefficient. It took Carnot to explain why doing that worked. But as is almost always the case, the engineers were ahead of the physicists. Engineers invent stuff, and then physicists explain how. I've also got lighting there as well in red. And there are wonderful papers on lighting, including one by William Nordhaus, economist who's been working in this area for many, many years, who doesn't quite understand, I think, what he wrote. But I've taken some of the data for this graph from his paper, some, I think, from other sources. And what you can see is that we are approaching the quantum limit of lighting efficiency. If we want to make lighting significantly more efficient, at some point we will have to bioengineer eyeballs and retinas and the cone and rod arrangements therein, because in the frequency range that we operate in, we are very close to the limit now. Okay, so the paper, back to the paper. how did the paper get written? This is an early doodle for the paper. And what I did here was on the back of electronic envelope, Excel, I always reach for Excel at times like this. I plotted the energy output, global energy output of wind, PV, and total primary energy on curves. And you can see wind here in red, we have a pointer. You can see, okay, let's try this. Yeah, okay, you can see PV is green, total primary energy is blue, and the residual primary energy, which is total primary energy minus the renewables, I predicted would do this. Now, one of the things that you can do is you can reflect on the likely consequences on the rest of the global economic system a few months after this happens. Okay. Basically, you've just built the biggest production chain ever to make all of this stuff as fast as possible. It's growing exponentially. So the rate, the capacity for producing PV, for example, is increasing exponentially all the way to here, and then it stops. Okay, well, nice to be able to turn this off at that moment. So there's a big bang. You can picture this as a flight path, a possible flight path to Heathrow. You wouldn't want to be on that aeroplane. Where are we? Okay. So, okay. So the conclusion from this is that the tentative conclusion from this is that constraints on growth at the end of a transition must mirror those at the start. At the start, we have a new technology, an insurgent technology, which slowly rises from next to nothing, starts to increase exponentially for complex reasons. The exponential function seems to emerge in all sorts of places in economic and industrial systems and human ecology, and indeed ecology generally, but in complex ways. It's not trivial. So constraints on growth at the end of a transition must mirror those at the beginning. You need a smooth asymptote. And in that case, real-world transitions must be S-shaped in some way. Okay? That is a piece of abstract reasoning. It is difficult for me to, it's impossible, I think, for me to prove that statement by collecting data and analysing it. I don't think that works. I think that is a piece of abstract reasoning which you either buy into or you critique. And if you want to critique it, we can critique it after this meeting and argue the toss backwards and forwards about whether real-world transitions must necessarily be S-shaped. Okay, where am I going? Whoops, I'm pressing the wrong button. Okay. Okay, so then I reflected on this and I realized that I had seen this graph in A New Scientist in the 80s. Okay, I thought, maybe I can use that because the report that this is based on, Dynamics of Energy Systems and the Logistic Substitution Model, by Marchetti Nakicenovic, was all about S-shaped substitutions, or partial substitutions. I will explain why partial later. I will talk about partiality of these. Okay, so here we are. The first thing to note about this graph is nonlinear axes and a rather peculiar measure of penetration of the new technology into the energy system as a whole. Marchetti and Nakicenovic did this. Let me just call them M and N, please, then I won't get mixed up. M and N did this so that they could, first of all, fit transitions, substitution processes, onto finite graph paper. So that was quite important. They needed to be able to boil all of this down into a single small piece of graph paper. And secondly, because the S-shaped functions that they were using appear as straight lines on these graphs until something else acts to prevent the growth of that technology and something else takes over. So what can we see? We can see a succession of technologies. Here we have wood declining. Okay. Interestingly, though, I'll come back to this in a few minutes, the world is using as much wood now, burning as much wood now, as it's ever done.
You stole my line.
I will have forgotten that by the time you reuse it. Please do likewise. Yes, indeed. Okay, then we have coal. Then we have oil, which really started taking off in the 1870s, thereabouts. Sorry, petroleum. There was always oil, but this is petroleum. And then natural gas, then nuclear, which got as far as this. That's about an inch on my graph, because that was the date of the report. Yeah? Okay. And the rest is projection, up the graph paper projection. This thing called sulfus, Marchetti and Nakicenovic thought there would be something after nuclear, by which they meant fission. They didn't know what it was going to be. So they said, well, maybe it will be solar, maybe it will be fusion. That means distant fusion and local fusion is another way of thinking of that. And so they called it sulfus. Moving on. Okay, this is what they wrote about substitution, which is generally unexceptional, except that you can disagree with bits of it. Substitution of a new way for the old way of satisfying a given need has been the subject of a large number of studies. One general finding is that almost all binary substitution processes follow characteristic S-shaped curves. Bottom, okay. Moving on. And the question that Paul Drummond and I had to face was, well, which S-shaped curve shall we use? And there's probably a chapter in most degree level maths books about logistic curves, because there's a number of different ways of making an S-shaped curve with algebra. I wanted something that had a small number of parameters, and because of my limited and declining mathematical ability, it needed to be simple. So it had to be something that I could understand, otherwise I can't use it. So this was the functional form that we chose, and things in quotes will be quotes from the paper. So let's just run through this very briefly. So what this means is that the penetration of the new technology into the energy system as a whole at time step t plus 1 equals the penetration at time step t times 1 plus alpha divided by 1 minus f at t, where alpha is a thing that I referred to as the intrinsic growth coefficient, or which is equal to the incremental growth coefficient of the insurgent technology when f is very small, at very small penetrations. At that point, you can see that that gives you, in discrete form, an exponential function. Yeah? If it's not obvious that that gives you an exponential function, find somebody at t who thinks they understand why that's an exponential function and ask them to explain it. It is very simple. Yeah. And then the extra tweak was finding a way to cope with more than one technology. So I wanted us to be able to include at least 2 separate technologies, insurgent technologies, in this analysis. And so we expanded this bit of the equation, basically by summing over the penetrations of all of the insurgent technologies. And that actually worked quite nicely. So, as it says here, this form is appropriate when the insurgent technologies are not competing with each other, but each competes with the previous energy, the incumbent energy system. These are all assumptions. Again, there is nowhere where you can put your thermometer or your temperature sensor and actually demonstrate that this is happening. These are all assumptions. This is a conceptually led paper. Okay, I've done that. You can come back to that if you want to, but yeah, okay. This is the share of the insurgent technology, and this, therefore, is the share of energy provided by the old fossil-dominated system, the incumbent technology. Good. Okay, then the next thing that we wanted to take into account was the fact that if you electrify things, they tend to become more efficient. So we built a simple we did a simple sectoral analysis of global energy use with, I think, about 5 categories. And I was able to persuade myself and Paul Drummond that the ratio of conventional primary fossil fuel energy displaced by a joule of electrical energy was about 0.7. In other words, there is a small energy efficiency gain from electrification at the global level across all categories of demand. And 0.7 is sufficiently close to 1 when you have rapidly growing, when you have high intrinsic growth rates, that it doesn't really matter. So we called that 1 to 1, just to make life easier. Okay, we tested a number of limits, possible physical and other limits, economic limits to the rate of growth of the insurgent technologies. We looked at the land and sea area occupied by wind and solar, which is an instructive thing to do, actually. I mean, it's almost worth doing it yourself. It doesn't take very long. And you realize very quickly that it actually matters where you put stuff. So in the same way, for example, that petroleum engineers tend to prospect for oil where they think there are oil-bearing rocks, it makes sense to put wind turbines where it is windy, and it makes sense generally to put solar panels where it's sunny. And that isn't always obvious. One of the funniest reports that you can read, I think it's still available online, is the Warwick Wind Power report, which is now about 20 years old, which was looking at the efficiency of urban wind and showed that some systems actually produced positive electrical output, but many systems used more electricity for their electronics than they actually produced, and so had were net negative producers of electricity. Don't put wind turbines in towns. It's daft. Okay, what else? Yeah, we looked at fraction of energy in global wind systems, fraction of incoming solar captured by PV, fraction of energy, wind energy captured by turbines, and so on and so on. You can read all of this. I think one of the more interesting ones that we looked at, but not as thoroughly as perhaps we should, was the ratio of cumulative metal requirements to reserves and resources. And I shall loop back to that later. Okay. Okay, here is a stylized S-curve using the function that we, functional form that we chose. And I've graphed this for an intrinsic growth rate of 20% per year, which is in roughly the right ballpark historically for wind and PV. Wind and PV growth rates have gone up and down over time. We graphed that because we wanted to understand or try to understand what the variability of growth rates had been. One of the things to reflect upon is the relevance of the transition from PV integrated into the earlier Sinclair pocket calculators, the 4-function calculators, and PV integrated into later, more powerful calculators, and whether the same processes would have been at work when that was happening in the 1980s. I was there in the 1980s, and as are happening now, as we're starting to integrate PV into grids at the gigawatt scale. My suspicion, I doubt whether the processes are the same. They may be analogous in some way, but they are not the same processes. So the idea that we can put all these data points on one graph and draw an exponential through them is bold. That's the word I'm looking for. Bold. That's a bold move. Okay, and I keep on reaching for the wrong button. Okay, there is the fossil output, and the horizontal line is years from the 1% share mark. Now, the awkward thing about these logistic functions is that they break down at the very low end because they predict an infinitely long tail going back into history of photovoltaics and wind and whatever the insurgent technology happens to be, and that is obviously not the case. Things must start somewhere. Declining effective annual growth rate. So the effective annual growth rate is the intrinsic growth rate modified by the declining share of consumption which is still available to be captured by the incumbent. F divided by 1 minus F. I did that because I was desperate for it to be a straight line, and it was a straight line, so I was happy. That meant that I hadn't messed up the maths in my spreadsheet. I am sufficiently mathematically challenged that I have to do these obvious checks to make sure I haven't garbled stuff. Okay. Annual increment of market share starts low, goes up exponentially, peaks, and then goes down. Is that obvious? That's probably obvious to some of you. Some of you might have to think about it. Okay, but it's a consequence of the idea that technology substitution is S-shaped. Now, I had a go recently, in the last few months, at estimating crudely the fossil fraction of investment. And I'm not quite sure what happens here. Yeah, there we go. The fraction of total investment which is being generated by the incumbent economy. If you think of the world economy now as actually coming in two parts, a renewable economy and a fossil economy. The fossil economy at the moment is providing most of the investment for the growth of renewables. That's just the way it is. I mean, the economy is big, it's complex, it's highly interconnected, and the idea that you can actually separate out the bit of the economy which is renewably powered is, again, bold. I like that word. I'm going to keep using that word because it's better than ruder words that I could use for that error. Okay, so support for the old from the new. I hope this works. Yes, I love it when that happens. Okay, what we're looking at here is the flow of investment from, and this, you have to interpret this conceptually. I don't know how you would measure this in practice, because as I say, the two economies are one, and I don't know how you distinguish between what is coming from fossil and what is coming from renewables that you've already installed. But I think that's justifiable. We can argue about it over tea. And this was, if you like, the punchline. I think this was figure 1 or something in the paper. And it looked like we got carried away with functions on this graph because there are too many. So let me see if I can explain what they are. Let me see if I can remember what they are. Okay, so the blue line here is total primary energy consumption for the whole global economy. The dashed line here is how that would increase if you decided to install significant amounts of carbon capture. And the technology that we had in mind here was DACS, direct air capture and storage. Okay. The reason for wanting to do that is that we wanted to say something about what hitting a net zero by 2050 target would mean in practice. And obviously with a logistic function, you can't hit a net zero by any when. Not by 2050, not by anyone else. So this was our rabbit out. This is a poorly integrated rabbit out of the hat, poorly integrated into the logic of the rest of the paper. We ran out of steam, but happily the reviewers ran out of steam sooner. So we were okay, and we got published. That's the trick in getting stuff published. You need to make sure the reviewer runs out of steam before you run out of steam. Then you get published. Okay, and we had 3 intrinsic. I shouldn't. No. Most of the pleasure that I got from writing this stuff was actually in the writing and in the spreadsheets and in the back and forth with Paul. And getting it published was the icing on the cake, but that's quite thin. There are 3 sets. There are 3 pairs of curves on here for different growth rates: low, central, and high intrinsic growth rates. And I think you can see that at the lower growth rate, you're not getting close to net zero until well into the second half of the century. So, I mean, I hope to be able to see this. I shall be 95 then, and I'm looking forward to seeing that. But I very much doubt if I'll see anything out here. So, but you might, that would be good. Okay. Okay, so more thoughts, and this is taken from the paper. The topology of the energy system and the nature of individual subsystems would likely alter substantially with high levels of solar wind. In other words, because coal mines and oil fields are not generally in the same place as it is sunny, some of them are, but not always, and they're also not generally in the same place that demand is located, although in some cases they are, you would expect the architecture, the topology of the whole global energy system to reorganize itself through this transition. And indeed, if you look at the transition into fossil fuels, that caused a massive reorganization of patterns of trade, of military power, and so on and so on, which I will say a few words about at the end of the lecture. Referee, how long before half time? I will get going. I'll get going. I can probably do this. Okay. Okay. So and this introduces, by the way, the idea of energy system architecture. I'm not going to say much about this because I'm running out of time, but all complex systems have form, have structure, have organization, have an architecture. I have an architecture. It's an architecture which was laid down essentially by the very first bony fish, which arranged to have two pairs of gills, the ones at the front and the ones at the back, okay, and a tail, which I've since lost. I've lost the tail, as have you, but it's kind of there in a vestigial form. We have an architecture. And the energy system, the global energy system, has an architecture. Okay. So going back to Marchetti and Nakicenovic's, you have to practice that. You have to practice Marchetti and Nakicenovic in front of the shaving mirror in the morning. Those of you who shave. Those of you who don't shave can borrow a shaving mirror and practice it. So this is what we called Solwyn, in a nod to Marchetti and Nakicenovic's Solfus. We thought we did know what it was going to be. Maybe we do, maybe we don't. What you can see is that it is certainly based on historical growth rates. It would be the fastest energy system transition ever to have taken place. And if you believe that there is graph paper out here to the left, it will be the first one that would go to something like completion. The others, none of them got past about 75%. Coal reached about 75% of global energy, but was then turned around by growing oil consumption and growing natural gas consumption. Okay, that's interesting. Where do we go next? Okay, I'm not sure where we go. Right, okay, so, yeah, but Solwyn has only just appeared on this graph. That's all the data we've got at the moment. And so it's fairly bold to just run that up the graph paper, even up the nonlinear graph paper. There is an earlier technology which showed early promise and then stalled, and that is fission, referred to here as nuclear fission. Yeah. So at these very low levels, technologies can come and go. And indeed, there is something about this graph which is about picking winners. So what we've done, what Marchetti and Nakicenovic did, and what Paul and I continue to do, was to focus on the technologies that we thought would win in the end. But maybe there are other technologies that we could find that could have gone on this graph that didn't in the end go anywhere. This graph, most of this graph is very backward looking. It's about history. And history always gives the impression of more inevitability than perhaps there really was. Okay, more comments from us. It therefore appears that the process of substitution is underway, which if continued, has the potential to displace fossil fuel from almost all markets between about 2050 and about 2070. Growth of solving could in principle be curtailed by an as yet unidentified insurgent technology, but such a technology would have to be growing even faster than solar and wind have been growing up until now. And I can't see it. I can't see it. Such a transformation of energy supply will both require and drive a deep reconfiguration of global energy demand towards electricity and derived products. It's self-dependent on multiple other technological substitution processes across subsectors and geographies. Reflection on historical transitions, first from biomass to coal and then to oil, suggests that such a process would profoundly impact patterns of global trade and ultimately geopolitics, domains in which human agency is key, but which lie outside the bounds of our analysis and are probably ought to be denied to a physicist of modest abilities who has been dabbling in energy for a long time but has never studied politics, geopolitics, or history formally. That's me, by the way. Yeah, okay. Press the right button. There are some lovely reflections in the Marchetti Nakicenovic report on the inevitability of energy system transitions. Here's a very good example. The smooth curves are two-parameter logistics assembled in a system of equations as described in the text. The fitting appears perfect for historical data. Anybody can make data look like a straight line by plotting it on logarithmic graph paper. Yeah? Almost everything looks straight, or at least sensible, on logarithmic graph paper. So, not so sure. The curves are now plotted, blah, 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 greatly helping visual inspection and formal considerations. The first fact to be observed is the extreme regularity and slowness of the substitution. It takes about 100 years to go from 1% to 50% of the market. We want all of this to be over in 50 years. We call this length of time the time constant of the system. Yes, historical transitions seem to have gone at roughly the same rates. We hope, don't we, that the transition to renewables will go 4 times as quickly. This regularity refers not only to the fact that the rate of penetration remains constant over such very long periods, but also the fact that all perturbations are reabsorbed elastically without influencing the trend. It is as if the system had a schedule, a will, and a clock. They've gone full on historical determinist here. It's really interesting, I think, what they've done with this. I suspect this stuff was written slightly tongue-in-cheek, but I don't know. I did have a conversation with both Marchetti and Nakicenovic very briefly, but we didn't get into this level. This transition may be different. First of all, it's global rather than region by region. So in the transition into fossil fuels, the first thing that happened was that Britain and then the US and parts of Northern Europe got into fossil fuels, and then other parts of the world followed, and so on and so on. Likely taking place in parallel with the emergence of other energy resource constraints and in the presence of the largest ever global human population. Okay, so it's not just energy which is in short supply or problematic, it is also things like minerals and so on. And moving on, the Hubbert curve. How many of you have read any of M. King Hubbert's papers? Okay, this goes on the list for all of our students. I won't suggest reading by my academic colleagues, but students, do please pick up at least one of M. King Hubbert's papers and read it. This is a 1971 paper, and he predicted that fossil oil, petroleum, would peak around 2000 to 2010 or thereabouts. I think I can't read the, yeah, something like that. And he's been proven wrong, but I think he just got the timing wrong. Okay, so there we go. So this is Lacherer, Hall and Bentley 2022. I said Lacherer was still publishing until very recently. He was, I think, 99 when he published this. How much oil remains for the world to produce, different methods. We don't know. To find out how much oil remains to be produced, we'd have to dig up the planet and analyze it, in principle. And everything else is an approximation, because we can't dig up the planet and analyze it. But this is what they thought. An additional feature of this is that the less oil is available, the harder you have to suck it out. The harder it is to suck the remaining oil out. And so the energy return on energy investment declines, and the energy cost of oil and gas extraction, which is this mustard-colored slice at the top here, grows. Here it was very small, you could hardly see it. In the early days, the heroic days of oil exploration in the 1860s, oil just came out of the ground on its own. Not quite sure where I was going with this. So we'll, oh, there we go. Yes, okay, yes. Geopolitical implications of all of this. First, just look at the top here. We've got OW. Wait for it. What on earth was that? OW? Opium War. Opium War 1, that was it. Yes, yes. Opium War 1, Opium War 2. They're coming now. Now I've got the Opium War. World War 1. In between, there was a couple of Crimean wars, which may in part have had something to do with the discovery of oil in the Crimea, or in that part of the world. World War II. One of the interesting things about World War I and II was that, certainly World War I, none of the participants wanted a war, with the possible exception of Serbia. But the major countries involved, it appears now, didn't want a war. And one of the saddest historical episodes was when the Kaiser, Wilhelm, decided to write to, I think, the Emperor of Austria, the Austro-Hungarian Empire, to say, please don't go to war with the Russians over Serbia. And because he was old school and wanted to do things the proper way, he sent a courier with a letter which arrived after World War I had started. It's worth thinking about, the unmanageability of conflict, particularly as it approaches and once it's begun. Gulf War I, Gulf War II, Ukraine. Okay, I would submit, Your Honour, that these are all aspects of competition between great powers for resources and are driven, first of all, by the upswing of fossil fuels in the 19th century and then by the decline of fossil fuels, and in particular oil, more recently. How much time do I have left? 3 minutes, okay. A bonus of writing this paper was that I took one of my spreadsheets where I was looking at the amount of replacement capital which had to be funded through the transition. So the early wind turbines have to be replaced by more modern wind turbines because they wear out and stop working. And when I stretched the first version of this graph past here, I discovered this interesting oscillation. And I thought to myself, that looks like Kondratiev waves, which I didn't know anything about, but I'd heard about. I'd seen a picture of Kondratiev waves. Kondratiev was a Russian economist in the early part of the 20th century who was very interested in oscillations in regional and national economies. Okay, there we go. That's from his 1926 paper, which he published in German, Die Leinenwellen der Konjunktur. And you can see that real-world oscillations are much messier than the very nice, simple oscillations on my graph. There we go, we'll ignore that. Things that interact here at the tail end of this transition are things like the physical lifespan of PV and wind systems. I took 15 years just to be able to show a graph, and the growth rate, the intrinsic growth rate. So that kind of illustrates that if you're lucky and you do some work like this, you'll discover stuff that you didn't expect. And I don't know whether I've discovered stuff that I didn't expect. I think there's something going on there. And if I find some time, maybe I'll dig into that more. Done. Stopped. References. The first one of which is Isaac Asimov's The End. Okay. please read Isaac Asimov's The End, which you can find going round and round on hard disks in a couple of places on the planet. It's a great short explanation of the foolishness of assuming exponential growth goes on forever. You'll enjoy it.